Ahí está grabando.
Good morning. This is the plane stress analysis for the point view of final elements signature. The students are Llanos Andy, Tenemea Dairo, and Villalba. This project is aimed to analyze the effective of a bracket which connects a deck beam with a side frame on a ship. For this analysis, both elements will be assumed as a plate, and with this load acting in the plane of them, this may use the solution for a plane space problems using finite element methods. Here we get the equivalent geometry from a depth ship structure, and we're gonna consider discretization according to the geometry. And with this discretization, we're gonna use the program provided for the instructor for solve and obtain the stress. So a plane stress problem is defined as a one in which the normal and shear stress in the direction perpendicular to the plane perpendicular to the plane of the plate are zero. With this information, we get the equations for a strain relation with the reflection in x and y. And according to the Hooke's law, the relation with the normal stress and shear stress and Poisson ratio. These differential elements need to be in equilibrium, and making a summation of forces. We get a simplified equation shown in the equation 3. And for solve this problem, we introduce an auxiliary function, the iris stress function. And so solving these two equations, we get the equation number 5. This partial equation of grade 4. And for solve this kind of problem, we use partitions with the triangular elements. These triangular elements provide the constants alpha, beta, and gamma, and the triangular elements provide the information necessary for calculate the area of that triangle. So with these constants and this area, we can make the stiffness matrix in a plane stress problem. This matrix provide the sigma in x and y direction, and using the minimal potential energy method, we can get the final stiffness matrix relation, the beta and gamma constants previously calculated. So for the methodology design, we have the structure dimensions. For this problem, we're going to use a fishing vessel with the following dimensions: length of 35 meters, a beam of 8.1 meters, a depth of 4.50 meters, a draft of 3.53 meters, and a block coefficient of 0.65. The velocity was approximated using information of the web for vessels with similar characteristics. This is the imaging of a original plane of the fifth frame of the ship. The bracket is located. The bracket we're gonna use for the calculate is in the left side. And using the equivalent geometry, we're gonna use only a quarter of a beam in the deck, and the half of the side So for this problem, we need to the external load. This external load, according to D&B rules, for this type of structure, is necessary to calculate the pressure acting in the surface. For calculate this pressure, first we need to consider the previous information, length, beam, and the velocity. So we get the following coefficients and values. And finally, using all these coefficients and all these values, we get the pressure acting in the deck. We have a value of 23.23 kilonewtons over meter acting in the deck.
Well, for the discretion, we use the Python program, and we with the libraries of the measures and MGH and the, well, first we develop discretion manually, but this is so laborious and only for 45 elements, and that's do of do of this we develop is necessary insert that program code. And for this case, the code develop a TX file in order in the format of the CSVAP program from Logan's book. The formats we for this case is the with 6 rows, and the and in that mentioning the number of elements, number of the joints, and the tip, the characteristic of that coordinate, and the position and the properties of the material, and the relations of the nodes with the elements. And first, for the discretion, we use 45 elements, and then we develop more partitions that is decreases the for this we decrease the size of the each the all elements, and we obtain more elements for discretion. And so the results we will obtain is the in the program from the Lugan is the parameters of the normal stress and in the x and y direction, and the deformations and the in the x and the y direction too. But we can see the graphs in 1, 2, 3. We see the order or the of the coordinates in the x and y direction is coordinates in the of the plate, the frame, but the in the other in the z axis is the is we can see that is according to the parameter. In this case is the normal stress that's in the order of the megapascals, and in the others graphs we can see the normal stress in y direction. That it is worth mentioning that the values on the z-axis indicate the values of the variables on their own axis, and it's not the values of the z direction. That is true for the for displacement. That's all indicate the sign or the no indicate this the way for will deform the plate, and only indicates the sign and will develop.
Okay, for our analysis of results, we can see the pictures here. For the normal stress in the x directions, the maximum normal stress is in the deck, and it's larger than from the line of Crujía. And for the normal stress in y directions is larger near of the bracket. Our analysis of results is is this, and it's according to the discretization, I carried out 3 different tests were obtained in which only the number of elements will depend of the area of each element. Therefore, the larger the area, the fewer elements, and vice versa. Regarding the analysis of normal stress in the x direction, it can see in graphs 1, 2, and 3 that the greatest efforts are produced from the bracket, increasing towards the baseline, and this makes sense modeling of element as a beam. In the left side and guided on the right side. In addition, these results are justified since there is a corner and the joint of the roof with the sign. Therefore, surface tension is produced, which can generate the break in said section. So the use of the bracket is essential since it acts as a support, decreasing this tension and in turn the incidence of stress generating a maximum stress value of the 129 megapascals in compression in element 43. Said element is specified in the annexes illustration 4, taking as reference the discretization of 45 elements. Now, if we analyze the stresses in the y direction in graph 4, 5, and 6, the part of element that is below the bracket is this one is affected. Since due to the load that acts on the roof, there is an accumulation of stresses in the elements of this section. According to the analysis of the deflection in the y direction are presented in the graph 7, 8, and 9, it can be seen that the deformations increase in the direction of the byline, and this makes sense since this section is where the greatest incidence. And for conclusions, we have the results of time are approximation of the real result of the frame under study, since an equivalent model was considered without considering the camber of the deck and the inclination of the side of the frame. According to the maximum values obtained for the forces in x and y direction, if we compare them with the maximum yielding stress of the steel, 235 megapascals. These are the minor and they do not cause structural damage to the frame. Regarding the sign change to appear in the results of time, it is concluded that the outer part of the frame and the bracket is in compression while tension is produced on the deck. For recommendations, for a future analysis, consider the camber and the inclination of the side to have a better approximation of the real model. Increase the pressure on the cover to know what the load limit will be according to the yielding stress. Analyze the results by increasing and decreasing the bracket dimensions and model the element of analysis in NCs to verify if the results of time are acceptable. And finally, in the event that the stress exceeds the allowable limit, it is recommended to perform a non-linear analysis with software ANSYS. Thank you.